We want to start by reviewing some of the bridges that Nehemiah showed in his video and talk a little bit about where tension and compression are in the various members of the various bridge types. So let's go ahead and take a look at those. The first bridge that Nehemiah talked about was the suspension bridge. In the suspension bridge, all the tension is primarily carried by the cables. You have two primary cables that are shown here as the curved or smiling cables, right? And you have your secondary tension elements, which are the vertical cables hung from the primary tension cables. Those are all these guys. The big cables, the smiling cables, again, are comprised of a lot of small cables wound together. And by doing that, we develop friction, which in turn yields us a higher tensile capacity overall. The primary compression elements in the suspension bridge are the vertical piers. That's shown here by the blue arrows. Right? Blue is everything in compression, red is everything in tension. The deck, which spans between the piers on any bridge, will have compression in the top and tension in the bottom. This is based on gravity's tendency to make any horizontal element want to bend, like a smile. The second bridge we looked at was the cable-stayed bridge. The cable-stayed bridge is similar to the suspension bridge in that all of the tension is carried by those cables. Those cables are strung back to the vertical piers, which again are your primary compression elements, shown here in blue. Just like with the suspension bridge, your horizontal beam spans between those, or deck spans between those vertical piers, have the tendency to want to bend in a U shape, which creates compression in the bottom of the deck and tension in the top of the deck. However, all of that is resisted by those tension cables running back to the vertical piers. In the video, Nehemiah hit on a very important and very helpful element to cable-stayed bridges, and that is that for construction, the cable-stayed bridge can be built off a single pier. If you build in one direction at the same time as the other direction, and at each interval run a new cable back to the pier and hit the corresponding point on the other side, then you can build the bridge in both directions simultaneously at the same rate. This can be done at each pier to the point where they all meet in the middle. The third bridge we talked about was the arch bridge. Arch bridges are common in older architecture because everything in the arch bridge is in compression. There actually is no tension. This was a common practice for the Romans. If you look at this example of the aqueduct, you can travel tremendous distances using materials like stone that are readily available and withstand the test of time. As Nehemiah spoken to in his video, the fact that all of this is behaving as rock, whereas stone would typically behave in compression throughout its lifetime, you end up with a bridge that will last for a very, very, very long time. These bridges are very heavy and so have a natural resistance to wind forces that would be against the bridge from the side during its lifetime. The next bridge type that we looked at with Nehemiah was the truss bridge. In the truss bridge, all the members are acting in purely axial force. By that, what we mean is no member itself is bending. Members are all either in pure tension or pure compression. Looking at this example here, you see that all of the top chord members are functioning in compression, again by the blue, right? As well as the vertical members, and that your cross members, your braces, are in tension. All of that is resisting the tension that's developed in the deck as vehicles or people move across that span. The next bridge type we looked at with Nehemiah was the cantilever bridge. In this bridge, all of the compression is carried by the central element of the truss or whatever you're using as your superstructure for the cantilever, and all of the tension is carried in the top chord of those cantilevered elements. These bridges are great for long span conditions, such as seen here, because again, similar to the cable stay bridge, you can build out from each point of fixity. Those fixed points of fixity, are the central piers, here and here. The last example, the very most common example that you'll see in the world today, is the beam bridge. It's a very simple construction, but it is limited by how far you can span from one pier to the next. Standard concrete girders like this and steel girders have limits. And so without the use of the cable stayed or suspended or superstructure above the bridge deck, it really limits you on how far you can get from one to the next. However, this is the cheapest bridge to build, and it is the most common bridge used today. In this bridge, similar to what we've talked about before, all the tension force is carried in the bottom of the beam, and the compression force is carried in the top of the beam. In today's world, a lot of times we're inducing tensile forces into the concrete before we set the beam up, because by doing so, we can pre-stress that beam to the point where when we load it from above with people and cars, we limit the deflection across that bridge to a withstandable amount or a serviceable amount.